So after studying this module, you shall be able to know how to test for the presence of autocorrelation. You shall also be able to learn graphical detection of autocorrelation. Then we will learn about the runs test for detection and few more tests like Durbin-Watson test for detection of autocorrelation, the LM test for detection of higher order autocorrelation. We will use the Q test for detection of higher order correlation and use Wallis test for detection of fourth order autocorrelation.
Graphical method. The presence of autocorrelation can be detected by looking at the residual plot. The graph of estimated residuals may be plotted in several ways. First, it could be that we can plot the residuals against time, or we can plot the standardized residuals against time. The residuals are standardized by dividing the residuals by the standard error of regression. That is, E standardized is equal to E upon under root sigma mu hat square. These standardized residuals have mean 0 and approximately unit variance. For large sample, they are also approximately distributed normally. We can also plot the residuals against their lag values. So, for an AR1 scheme, ET may be plotted against ET minus 1. The runs test. Runs test is a non-parametric test because it does not invoke any assumptions about the underlying distribution of the disturbance term. This test is also called Geary test after R.C. Geary, who first proposed it in 1970. A run may be defined as the continuous sequence of either a positive sign or a negative sign, which could be attributed in the residuals. The length of a run may be defined as number of elements in it. For example, we may observe residuals with the following pattern of signs, which could be we have negative, negative, negatives, then we may have positive, positive, positives, and then again we may have negative, negative, negatives. In this example, we observe 8 negative residuals, followed by 13 positive residuals, followed by 9 negative residuals, for a total of 30 observations. When we observe that a positive residual is followed by a positive residual for a large number of periods, and similarly, a negative residual is followed by a negative residual for a large number of periods, then we say that we are observing few but long runs. Positive autocorrelation is said to be present in such a scenario. On the other hand, if runs are short and change quickly, then we can say that negative autocorrelation is present. Geary has also proposed a test of hypothesis to check if the runs are indicative of autocorrelation. The test can be described in the following manner. Let N1 is the number of residuals with positive sign, N2 the number of residuals with negative sign. Let's say N is equal to N1 plus N2, which means the total number of observations, and R is the number of runs. Now R is asymptotically normally distributed with the following parameters. Mean of R, denoted as expected value of R, is equal to 2N1 N2 upon N plus 1. Similarly, variance is denoted by sigma R square and is denoted to be equal to 2N1 N2 into 2N1 N2 minus N upon n whole square into n minus 1. The null hypothesis that can be tested is that the residuals are random. A table for critical values of runs if n1 or n2 is less than 20 is also there. Durbin-Watson, which is DW or D-test. Durbin and Watson have defined the D statistic based on the estimated residuals of the regression. D is defined to be equal to sigma t from 2 to n in bracket mu t hat minus mu t minus 1 hat whole square divided by sigma mu t hat square. Sigma ranges where t is equal to 1 to n. This is our equation 1. The assumptions underlying the D statistics are as follows. First assumption is that the regression model includes the intercept term. The second assumption is that the explanatory variables are non-stochastic. The third assumption is that the disturbance term mu t is generated by the first order autoregressive scheme. The fourth assumption is that the disturbance term ut is distributed normally. Next, which is the fifth assumption, is that the regression model is not autoregressive. That means it does not include lagged values of the dependent variable as one of the explanatory variables. The last or the sixth assumption is that there are no missing observations in the data. Relationship between D statistic and autocorrelation. ut hat and ut minus 1 hat are said to be approximately equal since they differ in only one observation. Therefore, the value of D statistic mentioned in our equation 1 may be written as D is approximately equal to 2 into 1 minus sigma mu t hat into mu t minus 1 hat divided by sigma mu t hat square. In both these cases, the summation, as we said earlier, is over t. This is our equation 2. If we define rho hat as the estimator of rho, the first order coefficient of autocorrelation can be defined in the following way, where rho hat could be equal to sigma mu t hat into mu t minus 1 hat upon sigma mu t hat square, equation 3. D is approximately therefore equal to 2 into 1 minus rho hat. This is our equation 4. Because rho is between plus minus 1 and can be written as rho greater than or equal to minus 1 and rho less than or equal to 1, therefore we find that D is between 2 and 4 and can be written as 2 less than or equal to D less than or equal to 4. This is our equation 5th. From this 5th, it follows that if rho hat is equal to 0, D is equal to 2, which means no autocorrelation. Similarly, if rho hat is equal to plus 1, we get D approximately equal to 0, therefore positive autocorrelation. If rho hat is equal to minus 1, D is equal to 4, that means we have negative autocorrelation. To summarize, if no autocorrelation is present in the model, then the D statistic will take a value equal to 2. If positive autocorrelation is present in the model, then the D statistic will take a value close to 0. If negative autocorrelation is present in the model, then the D statistic will take a value close to 4. However, it is important to note that the sampling distribution of D under the null hypothesis of no autocorrelation depends upon the values of the explanatory variables. So, the critical values of D will also depend on the values of the explanatory variables. In order to overcome this problem, Durbin and Watson developed the lower and upper bounds of D, and they named these as DL and DU. The probability distribution of DL and DU does not depend on the values of the explanatory variables, and they have the property that D is between DL and DU, written as D greater than DL but less than DU. Using this property, the Durbin-Watson D test can be carried out to test for autocorrelation. The values for the lower and upper bounds of D are contained in the Durbin-Watson statistical tables. So students, what are the steps in Durbin-Watson D test? The first step is that find the estimated residuals after running the OLS regression. The second step is compute the value of D. These days, all statistical programs compute this value automatically. The third step is find the values of DL and DU from the Durbin-Watson statistical tables corresponding to the given sample size and the number of explanatory variables for a given level of significance. The fourth step is determine whether autocorrelation exists or not, and whether autocorrelation is positive or negative by carrying out the following hypothesis tests. The first of this hypothesis test is test for positive autocorrelation. Our null hypothesis now is that rho is equal to 0 versus alternative hypothesis H1, which is rho greater than 0. Null hypothesis in this case states that there is no positive autocorrelation. The second test could be for negative autocorrelation, where our H naught star is rho equal to 0 versus H1 rho is less than 0. In this case, null hypothesis states that there is no negative autocorrelation. The third alternative is test for any type of autocorrelation, which means positive or negative. Our null hypothesis H0 or H0 star in this case is rho is equal to 0 versus alternative hypothesis H1, which says rho is not equal to 0. Now, null hypothesis states that there is no autocorrelation, positive or negative. The fifth step is accept or reject any of the above hypotheses as per the following decision rule, which is for W or Durbin-Watson D test decision rules. In this case, you can observe we have the null hypothesis, we have the decision rule, and we have the conditions. So for hypothesis 1 of no positive autocorrelation against no positive autocorrelation, our decision is reject if D is between 0 and DL. For the hypothesis of no positive autocorrelation, our decision is no decision if the value of D is greater than or equal to DL but less than or equal to DU. Similarly, for second hypothesis, no negative autocorrelation, our decision rule is reject if D is greater than 4 minus DL but less than 4. Similarly, for the same hypothesis 2, which is no negative autocorrelation, we would have no decision if d is greater than or equal to 4 minus du, but is less than or equal to 4 minus dl. For the third hypothesis of no autocorrelation, our decision will be do not reject the hypothesis if d is greater than du, but is less than 4 minus du. Having learned the Durbin-Watson test, let us try to understand if there are any limitations of this Durbin-Watson test. There are some limitations, which are: the first is that the test is applicable only when the assumptions underlying the D statistic are fulfilled. The second is test can only be used for testing the presence of first order autocorrelation and not higher order autocorrelation. And the third limitation is that the test contains zones of indecision where it cannot conclusively determine the absence or presence of autocorrelation. We have the section 3.2 where we can now look at another test known as Durbin's H test. When the regression model is autoregressive, the D statistics in the Durbin-Watson test has a tendency to be close to 2. Thus, it has a built-in bias to accept the null hypothesis of no autocorrelation, even when it is not true. To get over one of this limitation, Durbin in 1970 proposed the H test. He said if there is an autoregressive regression model of the following kind, which is yt is equal to beta 1 yt minus 1 plus beta 2 yt minus 2, so on up to beta p yt minus p plus beta p plus 1 into x1t plus so on up to beta p plus k xkt plus ut, which is our equation 6, where ut is equal to rho ut minus 1 plus epsilon t, and epsilon is distributed normally with zero mean and variance sigma epsilon square. In that case, the value of H statistic is defined as under. H is now equal to 1 minus d by 2 into under root of n upon 1 minus n into variance of beta 1 hat. This is approximately distributed normally with mean 0 and variance 1, where the variance beta 1 hat is the variance of the coefficient yt minus 1, or which is you can say is the estimated variance of beta 1 hat. D is the Durbin-Watson statistics as defined earlier, and n is the sample size in this formula. Similarly, we have some steps involved in Durbin's H test, which we can summarize. So what are the steps? The first step is run the OLS regression for the model represented by equation 6. Then find variance of beta 1 hat. And then final step is compute H. The fourth is, since H follows a standard normal distribution for large samples, we use the normal distribution to carry out the following hypothesis test. The first hypothesis could be test for positive autocorrelation, where our null hypothesis is rho is equal to 0 versus alternative hypothesis H1, rho is greater than 0. In this case, null hypothesis states that there is no positive autocorrelation. The second hypothesis could be for test for negative autocorrelation. Now we can represent null hypothesis S0 as rho equal to 0 versus alternative hypothesis H1 as rho less than 0. So null hypothesis states that there is no negative autocorrelation. Let us understand the limitations of this H test. It is not possible to use this test if n into variance of beta 1 hat is greater than or equal to 1. Durbin's M test. Durbin in 1970 suggested the M test to overcome the limitation of the H test. The steps involved in Durbin's M tests are as follows. First, run the OLS regression for the model represented by equation 6. Second, obtain UT hat. Third, run the OLS regression, which can be written as UT hat is equal to B1 YT minus 1 plus B2 YT minus 2 plus BP YT minus P plus BP plus 1 X1T plus so on plus BP plus K into XKT plus BP plus K plus 1 into UT minus 1 hat. This can be defined as our equation 7. We use the t-test for the coefficient of UT minus 1 hat to carry out the following hypothesis test, which is the first could be test for positive autocorrelation, where again we write null hypothesis as H0 is equal to rho equal to 0 versus H1 is rho greater than 0. So null hypothesis states that there is no positive autocorrelation. The second is again same, which is for test for negative autocorrelation, and H0 is rho is equal to 0 versus H1 is rho is less than 0. In this case, null hypothesis states that there is no negative autocorrelation. Wallis test. Wallis proposed a test for fourth order autocorrelation. If the disturbance term is characterized by fourth order autocorrelation, then we can write UT is equal to 5,4 into UT minus 4 plus epsilon t. Hypothesis in Wallis test. Our null hypothesis now is H0 equal to 5,4 is equal to 0, whereas alternative hypothesis H1 is 5,4 is less than 0, or hypothesis H1 is equal to 5,4 greater than 0. 5 is our symbol in these cases. Essentially, the null hypothesis states that fourth autocorrelation is not present, and the alternative hypothesis states the converse is true. Steps in Wallis test. So let us understand what are the steps involved. Wallis proposed a modified D statistic, whereas D4 now is equal to sigma UT hat minus UT minus 4 hat whole square, where summation is from t equal to 5 to n, divided by sigma, where t is from 1 to n, into UT hat square. The test can be used with or for a model without intercept, which contains dummy variables for quarterly data, or for a model with intercept and without dummy variables for quarterly data. Wallis derived upper and lower bounds for D4. Tables for different significance points have been derived separately for both these models. Let us now look at another test known as Lagrange multiplier LM or Breusch Godfrey test. This test overcomes two main limitations of the Durbin-Watson test, namely It allows the use of both autoregressive and moving averages regression models. Second, it allows testing for higher order autocorrelation. So, what are the hypotheses in LM tests? The null hypothesis is that there is no autocorrelation of any order. The alternative hypothesis in this case can be of two types. One, in which UT is generated by the pth order autoregressive, that is ARP scheme, as follows. We can write UT equal to rho 1 UT minus 1 plus rho 2 UT minus 2, so on up to rho P UT minus P plus epsilon T, where epsilon T again is assumed to be distributed normally with mean 0 and variance sigma epsilon square, and covariance between epsilon T and epsilon S is equal to 0 for T not equal to S. The other hypothesis, in which UT is generated by the pth order moving average MAP scheme, could be as follows. UT is equal to rho 1 epsilon T minus 1 plus rho 2 epsilon T minus 2 plus so on up to plus rho P epsilon T minus P plus epsilon T, where epsilon T again is distributed normally with mean 0 and variance sigma epsilon square, and covariance between epsilon T and epsilon S is again equal to 0 for T not equal to S. Steps in LM test. So let us understand what are the steps involved into Lagrange multiplier test. First is to estimate the model by OLS method and obtain the estimated residuals UT hat. The second is run the auxiliary regression. The third is that we estimate UT hat equal to alpha 1 plus alpha 2 xt plus rho 1 hat UT minus 1 hat plus rho 2 hat into UT minus 2 hat, so on, plus rho n hat into UT minus n hat plus epsilon t. This is our equation 8. The third step is obtain R square, capital R square, or which is also known as the coefficient of determination. The fourth step is the test variate is, in this case, it is n minus p into R square. So that is our test criterion statistics. The fifth step is for a large value of n, n minus p into r square is distributed as chi-square with degrees of freedom p. The hypothesis test is a test of joint significance of first n autocorrelations of these disturbance terms. So our hypothesis is that H0 is rho 1 is equal to rho 2, so on up to rho n is equal to 0, no autocorrelation. Alternative hypothesis H1 is at least one of the row is not equal to 0, which means autocorrelation is present. The same test can be used for any one of the alternative hypotheses. The seventh or the last step is if the test statistic exceeds the critical values of chi-square at the chosen level of significance, then the null hypothesis is rejected. Advantage of LM test. The test can be used both for autoregressive and moving average autocorrelated disturbance term in the model. Limitation of LM test. A limitation of the test is that the length of the lag P cannot be specified a priori. The length of the lag has to be found by inspecting the T statistics on each lagged residual in the auxiliary regression. So we have another test known as box-Pierce Q test. Students, this test is based on the following Q statistic, which is also known as box-Pierce Q statistics. Q is equal to n sigma rho k hat square, where sigma is k equal to 1 to h. So n is the total number of observations and h is the maximum lag in this case. Rho hat is the estimated autocorrelation function known as ACF, and it is given as rho k hat is equal to sigma ut hat ut minus k hat, where sigma is where t is equal to k plus 1 to n upon sigma ut hat square. Summation is where t is equal to 1 to n. Ut hat is the estimated disturbance at tth observation. So in this case, if residuals are white noise, the Q statistics follows a chi-square distribution with h degree of freedom. Let us understand the limitations. It has been found that this Q statistics in box-Pierce test performs very well with large samples, but not with small samples. The another test is Ljung box Q test. The Q statistics in box-Pierce test has been modified so that it performs well in small samples. It is known as Ljung box Q statistics. The Ljung box Q statistics is equal to n into n plus 2 summation over k into rho k hat square upon n minus k. The summation over k is from 1 to h. In this case, rho hat is same as box-Pierce Q statistics, and h is the number of lags being tested. If the residuals are white noise, the Q statistics follows a chi-square distribution with h degrees of freedom, just like the box-Pierce Q statistics. The Q statistics can be applied for any type of ARIMA, which I am sure all of you know is autoregressive of integrated moving average model. But when it is applied to test for autocorrelation of the disturbance term in a model, the degrees of freedom of the test statistic have to be computed by subtracting the number of parameters from the total number of observations. Hypothesis in Q tests. The null and alternative hypotheses are the same as those in the Breusch-Godfrey LM test. So let us understand the steps in Q test. They are, the first is estimate the model by OLS method and obtain the estimated residuals UT hat. The second step is estimate the autocorrelation function rho hat. Third is compute the test variate Q. The next step is that Q is distributed as chi-square with h degree of freedom. The fifth step is the hypothesis test is a test of joint significance of first P autocorrelations of these disturbance terms. And our null hypothesis is that rho 1 is equal to rho 2 up to rho n equal to 0, which means no autocorrelation. and our alternative hypothesis is at least one of the rows is not equal to 0, which is autocorrelation is present. The sixth step is if the test statistics exceeds the critical value of chi-square at the chosen level of significance, then the null hypothesis is rejected.
So let us now summarize what we have learned so far. There are several methods for detecting the presence of autocorrelation. I am sure you can all appreciate it. The graphic method and the runs method are non-parametric tests. They are also by and large indicative tests. The Durbin-Watson test and the Durbin's M and S tests are parametric tests that can be used for detection of first order autocorrelation. Wallis test, LM test and portmanteau tests are used for detection of higher order autocorrelation. Durbin-Watson test is one of the most commonly known tests for autocorrelation, but it suffers from some limitations. These limitations are that in some cases the test is inconclusive because we have an inconclusive range. The test can only be used when the regression model has an intercept term and does not include lagged dependent variables. The test can only be used when the error term is autoregressive. Durbin's S test helps in using or testing for autocorrelation in the presence of lag dependent variables in the regression model, whereas the Lagrange multiplier test can be used when the error term is generated by an autoregressive or moving averages process.